What's that?
Sometimes I use those, so I'm not sure. Seems like
Well, at least somebody does. I'm like, I got so many videos that have
selfish reasons.
zero views. I'm like, oh, okay, just taking up space somewhere. Let's see. So watch. Let's do one thing before it kind of leads into what I'm talking about. It's on this paper. Let's see if we can quickly do this. Now watch. This is kind of nifty. Let's actually attack this thing with the definition. And remember, we already know what this is. We did this the other day, and I know we already know what this is because it's on the paper, but I haven't proven it yet. This one was just 1 over s squared, right?
Yeah.
So to do this, you can kind of realize that you would go insane if there wasn't some kind of a recursion formula that happens very quickly. Because what the hell's n? Whatever the power is determines how many times you're going to have to do by parts, doesn't it?
Yeah.
And it's n. So, what the hell's that mean? What's going to happen to me? So how would I do by parts? I would definitely do what? You would definitely be to the end, because that's the one that's not cyclic or not repetitive. When it was e and cosine and e and sine, who gave a shit which one you called what? They were both cyclic in a way, right? So du is, then dv is the other piece. So v is
Over negative s.
I like it.
Just over s.
Beautiful. So then we get gather interval. We get uv. So we get negative t to the n e to the negative st over s from 0 to infinity minus the integral of v. There's a minus there already. Du. So I get over s. There it is. Get out of there. Get in there. All right. Now what is this? I don't know if you guys remember that. Let me see if you guys can tease out what happens here. Let me just rewrite this. This s doesn't mean shit, right? I mean, it's a constant in terms of t. What would I use? What form is it in right now? If I let t go to infinity, it's on the form of what? Infinity. Yeah. Yeah. If you use L'Hopital's rule, I'm not going to. You don't have to do this. The more you know, the less you have to do. Which one's going to die if I use L'Hopital's rule the right number of times? Or not die, but go to 1 eventually. The top. The bottom is going to basically stay the same. I keep plucking off extra constants. Who gives a shit when I'm going to infinity, right? So this is going to become 1 over that, which is 0. I like it. And then when you plug a 0 in, you get, do it. You get 0. All right, I like it. So that is all 0. How do you guys feel about that?
Can you explain that one more time?
Yes.
Okay.
So if it was just t over this, forget about the s, and you're doing the limit as t goes to infinity, right? You could use L'Hopital's rule, right? So that would be, after one iteration of L'Hopital's rule, it becomes 1 over s e to the st, which is 1 over, yeah, and that's when I did the BFN for my students that didn't understand that you really can't write 1 over infinity.
Right.
It doesn't make any sense. And I kept doing it anyway. So I'm like, use this big freaking number. And I used a different f, but over.
So we get 0.
0. All right. If this was t squared, when I just used L'Hopital's a couple times,
Yeah.
it would still eventually be 0. So no matter what the hell, if it's n, isn't that going to be the same thing? I just have to do it enough times. All right, I like it. And by the way, n here has got to be greater than or equal to, well, greater than, I can't remember where we're going to end up. At least greater than 0, if not equal to 0. Okay, so this is 0. And then here, what is this? Can you guys identify that? Write it a different way. What was this? It was the Laplacian of t to the n. So what is this? The Laplacian of t to the n minus 1. So now we've got the Laplacian of t to the n equals n over s Laplacian of t to the n minus 1. What do I want to change that? There. So what's the Laplacian of t to the n minus 1? Using this rule is equal to n minus 1 over s Laplacian of t to the n minus 2. You guys see what's happening? No? All right, again. So what's this rule say? Laplacian of t to the n. The n seems to come down and it becomes n minus 1 over s. All right, so what's going to happen for this guy then? Using the form of that rule. N minus 1.
N minus 1.
T to the n minus 2. So this then is equal to n times n minus 1 over s squared Laplacian of t to the n minus 2. Now if I kept going, do you see how I get the actual result for this? Which is, on your paper, I can say, let me get this out of here, this is the definition. Let's just put the actual end result up here. What was S to the n plus 1, right?
Oh.
Yeah.
Oh.
Do you guys see how that's going to eventually happen?
Yeah.
Oh, yeah.
Hopefully. All right. The book has a slightly different approach to explaining it, but I don't know. Either way works the same, to be honest. But this is very straightforward. Because then n minus times n minus 1 times n minus 2 until you get to 1. Isn't that n factorial?
Yeah.
And you will get one more s on the bottom, because when you get to Laplacian of t, what's that? It's 1 over s squared. Do you guys get that? You're going to have one more s on the bottom because of that, really. No, yes, not at all. What the shit, Jeff? Anyway, all right. I was just trying to explain why this is true. You've got that as a true statement now on that chart. This is really kind of nifty if you let it be. Because if you define the Laplacian, if you work something out and you get another Laplacian, you just created a relationship between two Laplacians, and that might be useful. Like we did with Laplacian and cosine earlier. We just put the Laplacians together, and it was useful. Here, it's almost a recursion relation, right? So it is, really. And then I can get this in the end. Okay, all right. Is there anything else in that? I don't really want to play with the Ascension Coach too much, because most of us don't know much about it. That sucks. Note, since this is all based on integrals, that last thing should be pretty self-evident. Any constants can just kind of dance in and out, just like they can with integrals. And the same thing with the inverse Laplace. Okay, now, here's what I was talking about. This is, let's see. So you guys got all this if you want it? Or as much as you wanted? Okay. You had me at blank board. All right. So what's the inverse Laplace of n factorial over s to the n plus 1 then? To the n. So, start off nice. What's the inverse Laplace of 2 over s cubed? Can you identify what n is? N is 2 by this. So what's got to be on the top? 2 factorial, is that there? 2 factorial is 2. So yes, so this is equal to t squared. See how you identify what n is. That's the important thing in the form. Now the other reason it's important to do that is because what if I don't have what I need up here? So for example, what's the inverse Laplace of, I don't know, Jeff, 15 over s to the 5th. Who would like that one? See how far you guys can get with that. have to take something out also. So let's see if we can get this. It should feel a little bit like the integration stuff you have to do for U sub, balancing things.
Is it 3 factorial?
Yeah, so what's n?
4?
4. So what do I need on top?
4 times.
Yeah, I need 4 times 3 times 2 times 1. I have a 3. What do I have that's extra? What's extra?
5.
5. So let me take a 5 out. Right? And this is Laplacian. Let me see. Inverse Laplace. Take a 5 out. Now what else do I need up here, though? What do I need up here that's not here? I have the 3, so I need the 4 times 2 times 1. So I need to put this over. So let me do it like this. I took the 5 out. Is that cool?
Yeah.
I need 4 factorial on the top. So I need 4 times 3 times 2 times 1, times 1, who cares? So this better be, I had to multiply by 8, so I better divide by 8. Now if you're one of those lucky people that had a teacher that taught you U sub, so you didn't solve for frickin' dx, or du, or whatever, right? You didn't solve for dx and you just plug the shit in there and pray, that's bullshit. You actually balanced it. You need a 2, you put a 1/2 in front, so you balanced it. Because those teachers realized you needed something like that for this shit. So I need an 8 inside, I better put an over 8 outside. Balanced, right? And on the bottom I got s to the 5th, which is what really, I don't need anything down there, it's what kind of tells me what to do. So what does this become? 5/8 what? I'm going to love the fact that my 5s look like s's.
5 over
2 to 3 factorial.
T to the 4th.
That's 15 over S.
S to the 5th, by the way. Yeah, it's really exciting. Do you guys get the idea of, I can't really mess with this. I can't give it more s's. But I can certainly give it more, or take some numbers away. So this sets up what n is, and the form tells me what I'm supposed to have on the top. So then I make that happen by balancing. I need 8, I better divide by 8. There's an extra 5, I'll just take the damn thing out. All right, let's try one more of these. Based on this guy. Let's see, where did I write that? There. So what's the inverse Laplace of, what you got, Jeff? Let's do 2 over s squared plus, 64, I like it. What's the variable inside the inverse Laplace? What's the variable of that function inside the inverse Laplace? S. So which one of these has a variable on top? Cosine. Does this have a variable on top?
No.
So it must be sine. I like it. So what's wrong up there? What's k gotta be?
Oh, 8.
K's got to be 8. So you identify what tells you what the hell's going on for sure. I know K's got to be 8. And so what's the top supposed to be? 8. So what's it missing?
4.
So how do you put it in there?
1 over 4.
Yeah, 1 over 4, inverse Laplace of 8 over s squared plus 64. Now that becomes exactly,
So it's close sine of 18.
yeah, K is 8. Cool. So you guys see that? So again, it's all about what part of this is going to tell me what n is or what k is, and then that tells me what else I need in other places. So cool? All right. Okay, maybe that's enough of this. Maybe I should let you guys try some on your own. Yeah. So try to force yourself to only look at this side. Don't worry about the back yet.
Okay.
It's not interesting. It's the side that says Laplace transform practice. I'm trying desperately to get us to a point, because I know right now this might be a little frustrating in a sense that, yeah, this is great. I'm learning all this weird S&T shit. What's it do for me? Again, it solves DEs so beautifully, but that's We gotta get used to how it works first.
You want us to use the shortcut way or actually solving the whole thing?
No, just use the chart.
Okay.
You're gonna have some homework problems that make you do that, and you know I'm gonna put something like that on a quiz or a test, so. Did I give you a blank one? I'm so nice.